Recording going.
Oh, I forgot to ask you these questions on Tuesday.
Well, this is a perfect time.
So they're like kind of in relation to the homework. After I saw some of the answers, I was like, they didn't make sense to me, so I wanted to ask. What is the difference between an amine and an amide?
The difference between an amine and an amide. No, it's okay. You're learning how to pronounce these things. They're weird pronunciations. An amine is anytime you've got a nitrogen attached to an R group, to a carbon, right?
Okay,
Generally, it might just be, this is a primary amine, but you can also have more than one carbon attached.
okay,
Right, so that would be a primary amine, this would be a tertiary amine, so we kind of rank them like we do with carbons. An amide has to be adjacent to a ketone or to a carbonyl, really. So this would be a tertiary amide. This is a primary amine. So kind of like how a carboxylic acid is taking a carbonyl and you put it next to an alcohol. An amide is you take an amine and you put it next to a carbonyl.
okay, got it. And then I had never heard of a haloalkane.
Haloalkane.
Yeah. I had, like, last year I had learned it as an alkyl halide, so that's what I had. On
Let me
my
go back
flashcard.
because an alkyl halide works just as well.
Okay.
That is just as correct.
No idea what that word means.
Yeah, I
So they're the same?
missed, yeah. They're the same thing.
And then you answered my third one with the sp2 carbons. So that was it. I just wanted to ask those before I forgot again.
No, that's perfect. It's exactly the right time to do it. So today's lecture is gonna be short.
Okay.
And instead of calling it a quiz, it's a little bit longer this time, so I'm gonna call it more of a homework assignment, but we'll probably finish these slides in the first hour and 15.
Okay.
And then, so then I'll just turn you loose for the week and you can work on the homework assignment. But it's basically, the homework assignment is it's all on Canvas. What's, oh, it's gonna make me do the two-factor authentication, but that's okay.
Multiple times.
So,
Sue would do this, but she'd forget her phone downstairs in her office. So she'd try to sprint down to get it before it timed out. It never worked. She always had to redo it.
yeah, I have the advantage of commonly wearing pants that have pockets large enough for my phone.
Just a guy on your pocket size.
It's almost like fashion is designed to favor males and not women.
Unfortunately.
Maybe it's just me, but I've never thought to myself, you know, I wish that these pockets were useless.
I wish these pockets were fake, actually, and then I couldn't put anything
Oh,
in them.
I love those. It's just like, looks like a pocket.
Yeah, no, that's the word. And I even catch some of the negative aspects of that because I get told to hold phones and wallets all the
Yeah.
time now.
Yep.
Anyway, there we are. So assignment, I linked it in.
I saw it come
Three.
through today this
Okay.
morning.
So it'll be due on Sunday, just like one of the quizzes.
Yeah.
But it's just a little bit longer. So, and since it's all drawings and stuff like that, I just figured might as well just make it a homework assignment, put something in the assignments category. I even tried to print it out for you, but my new computer is still fighting me on printing things.
Okay.
So I have to get that sorted out, but I can see a printer and I printed to it before, but I can't print to it from Word.
Interesting.
And I didn't have time to put the document into some other thing to make it work, so. but it's on canvas. So you'll be able to see it there. And at break, I can go see if I can make it print better. All right. So we're gonna talk more about acids and bases today. So a reminder, this is where we ended last time. I just want these to go away now. There. So let's look at, we did that practice with propranolol or whatever it was. That same approach works for any functional group. So if we looked at, say, an amide, amides are on here, right? Amides are not on here. If we looked at an amine, it's an amine because it's one carbon away from the ketone versus a carboxylic acid versus the alkyl hydrogens. What is our most acidic? Our most acidic proton. What functional groups can we find here that show up that are similar to something on this chart? So that's our carboxylic acid, right? So that would be very similar. So that's called an alpha carbon. Yeah,
Second.
we don't have the second one, but still, let's say that that's still going to be something similar
Okay.
versus the nitrogen. But it's not just an alcohol group, though, it's an alcohol attached to a carbonyl, which makes it a carboxylic acid. This whole thing collectively is a carboxylic acid group. So those carbonyl groups are a little bit tricky because they're more than the sum of their parts. You can't just say it's a carbonyl with an alcohol attached. I mean, it is, but it behaves in a unique way. So we call that a carboxylic acid. And how do these pKa's work? Closer to the top left made it a more acidic. So if these are our three functional groups, our carbon here doesn't look exactly like this, but either way, it's going to be, that's going to be our most acidic group that we have. So if we're going to pull a hydrogen off of this molecule, which actually, you know this molecule, this is glycine. The amino acid. Have you talked about amino acids in biology yet? But you didn't have to learn their structures or names. I guess that is more of a biochem thing. So when you get to upper division biochem, you'll have to memorize all of the amino acids, structures, and names. This one in particular is glycine. Glycine only has, you talk about the R groups on an amino acid. Do you remember talking about that at all? Very vaguely. Basically, the R group, so an amino acid is more specifically called an alpha amino acid because there's an amino group on the carbon that's one away from the acid. So they all have this general shape. The difference between the different amino acids is what's attached there. That's what we call the R group. If that R group is a hydrogen, it's glycine. If that R group is something else like I want another carbon, if it's in a CH3, a methyl group attached there, that's alanine. You took a benzene ring and stick it on that carbon, you get phenylalanine. So all of your amino acids and therefore all your proteins in your body are all built on the same basic structure. And then you link them together to make an amide. And that's how you get these big long chains of amino acids. Anyway, I was just drawing a structure at random and I happened to draw glycine, so. Digression time. All right, so here's one of the ways that it matters, that pKa matters the most in organic chemistry. In organic chemistry lab, we do a ton of, almost everything we do is either mix stuff together to have a reaction happen to make something we care about, or there's some molecule that naturally occurs and how do we extract it? So we're gonna do a lot of extractions in OChem lab. An extraction is basically, the simplest type of extraction you can think of is like making tea or coffee. Making tea and coffee is a hot water extraction. You're literally pulling all the organic compounds out of out of a biological system. If we took coffee and tried to extract just the caffeine from it, that'd be more of a targeted extraction. We're trying to pull the caffeine out and leave everything else behind. That's still just a form of extraction. And one of the primary ways that we can control what gets extracted is by using solvents where some things dissolve and others don't, basically by playing around with solubility. So in general, nonpolar compounds aren't going to dissolve in water, right? How do we tell if something is nonpolar? If I have this big long molecule, is that polar or not?
Electronegativity.
We don't even need to though, really though, right? Because what's oxygen? Oxygen's on our big long chain, right? Or on our Mount Rushmore. And everything else is carbons and hydrogens, which is our definition of nonpolar. But we've got polar bonds and we've got asymmetry. So it is technically a polar molecule. The thing is, in organic chemistry, we're going to wind up seeing that almost all of our molecules are polar by that definition. Our definition of polar in terms of OChem is generally, will it dissolve in water? If it dissolves in water, it's a pretty polar molecule. And if it doesn't dissolve in water, even if it meets this criteria, we usually would call it nonpolar. Because even though we have part of this molecule that is polar, this part of the molecule will dissolve in water. The rest of this won't. This whole section is nonpolar. And so turns out there's like a crossover where even though this is a polar molecule, it won't dissolve in water readily. And the longer this chain gets, the less it's going to dissolve in water. So in general, the rule is you need at least one OH group per 5 carbons for it to be considered soluble in water. So this would dissolve, but it wouldn't dissolve well because we're getting close to that threshold. One of the other ways we can control whether something dissolves in water is by protonating or deprotonating it though. Because when you protonate something or deprotonate it, if we deprotonated this alcohol, it's not a terribly acidic group. We think back to that last group, that last chart, all of our alcohols were down here in the 15 to 18 range. So it's not something we would consider to be acidic per se, but we can pull that hydrogen off. And when we pull that hydrogen off, we get a molecule that's going to look like this instead. Now it's not just polar, now it's charged. So if you think back to last week's part of the lab, when we did those solubility tests, the benzoic acid wouldn't dissolve in water, right? Benzoic acid is just benzene with an acid group attached to it. Draw the complete structure as we're still getting used to this. Are you starting to get good at drawing hexagons yet?
Getting better.
One of my favorite chemistry memes of all time is the Gaston reading the book.
Oh, yeah.
meme. How do you read this? Organic chemist, how do you read this? There's no hexagons. So benzoic acid wouldn't dissolve in water. But it will dissolve if you try to put it into an alkaline solution. If you deprotonate it, basically pulling that off and turning this into a negative charge. Once it's charged, that's going to be even more soluble in water. We would normally expect, well, it's got an acid group, it's got all these polar bonds, maybe it'll dissolve in water a little bit, but it's got this whole hydrophobic region of the benzene ring. So when we observed it, we didn't see it dissolve well. If we put it into its deprotonated form, into the conjugate base, it dissolves really well to the point that it gets added to all sorts of food products because it's actually a really good preservative. So when you took nitrate, let's do a little bit of review on nomenclature for acids. What's this molecule or ion?
Nitrate.
And if it's protonated to make it an acid, what is that called?
Starts with an, it's like something nitrate, but it starts with an H, right?
No. So the acids based on what the ending was, we turned 8, got turned into ic, right? So this was nitric acid. Well, when this was protonated, it was benzoic acid. So reverse engineer that name. What is benzoic acid when it's deprotonated?
Benzate.
Close.
Benzate.
Benzoate.
Oh, wait.
You ever heard that term before?
I don't think so.
You read the instructions or read the ingredients on pretty much anything that's packaged. It's got sodium benzoate added as a preservative because it's relatively harmless to humans, but it keeps things from going stale and it keeps bacteria from growing. So it dissolves really well. The reason that we would add it to food is because we could dissolve it in water pretty readily. So sodium benzoate dissolves in water, benzoic acid doesn't. And the only difference between the two is whether it's protonated or not.
Would it ever spontaneously jump back to benzoic acid?
It will, because it's an equilibrium process, right? This is a weak acid reaction. So if you had benzoic acid in water, it will spontaneously deprotonate to make the benzoate and hydronium. But that's an equilibrium reaction. And that's a pretty small Ka. I want to say the Ka for this is in the like 5 region. So it's similar to acetic acid, but 10 to the minus 5 is still not that acidic. the other way of thinking about pKa, where this winds up being really useful is if you remember this equation. I told you we were gonna use the buffer equation. We're not gonna make buffers with it. This is also a really good way to look at the pH and estimate whether your compound is protonated or not. Because what happens if you have equal amounts of the protonated and the deprotonated? What happens to that ratio?
One.
It's just one, right? What is the log of one? 0. So when these two concentrations are equal, this whole term goes to 0. So, which is another way of saying what this line says. If your pH equals pKa, should be a comma there, the acid is 50% ionized or 50% protonated versus deprotonated. So if 50% of the of the acid is protonated, that means 50% of the acid will be soluble in water at that point, right? So basically what this does is this gives us a way to estimate whether or not we want to make the solution acidic or alkaline in order to increase solubility. Because if, let's say we wanted the benzoic to dissolve in water, which form do we want it in? Protonated or deprotonated? Deprotonated. So benzoic acid should dissolve better in basic or acidic solutions. Basic. If it's in a basic solution, that means your pH is greater than your pKa. Or the other way of saying that, if it's more basic than your pKa, you don't have very much H3O plus to go around. You basically, we have this equilibrium, but we're running out of H3O plus, right? And think of Le Chatelier's principle. If we're adding a bunch of hydroxide to this, we're using this up, right? It's gonna go away. What does Le Chatelier's principle say about equilibrium when you do that? Is it gonna shift to the right or the left? Why?
No, it's just, but I.
You had a 50-50 shot?
Yeah.
If we take away, if it's balanced and then we take away some of the product, we have to make more product to get it balanced again, right? So basically, if you add a bunch of hydroxide, if you make it more basic, you're gonna favor deprotonating things. If you make the solution more acidic, you're gonna go the other way. If you make it more acidic, you're adding more of the product. So it's gotta shift left to undo that, to get more balance, right? The other way you can think about it is when something's acidic, there's lots of H pluses around, so you're more likely to protonate something. If it's basic, there's hardly any H pluses around, so you're more likely for it to be deprotonated. So we just did this one, benzoic acid. The ionization of benzoic acid in water. You write it here. If the pKa of benzoic acid is 4.2. If the solution has a pH of 7.2, is more of your acid protonated or deprotonated? it's in a more basic solution, so you're gonna see more of it in the deprotonated form. Also, just to clarify, ionized and protonated are talking about two different things. I use them as sort of this is a little bit of a false dichotomy. Because something can be ionized or unionized. That's talking about the overall charge, right? And something can be protonated or deprotonated, and that's talking about, does it have the H plus attached? So really, these two terms, I made a typo kind of when I wrote this slide. Because it should be ionized or unionized, or protonated or deprotonated. These are sort of talking about two different things. They're both important. And in fact, when we're talking about whether something dissolves in water, that's more important, is whether it's ionized or not. But different functional groups are ionized when they're protonated versus deprotonated can be different. Acids are ionized when they're deprotonated. Amines can act as a weak base. So amines are going to be more soluble in water when they're protonated versus deprotonated. So there's a little bit of a back and forth there we have to pay attention to. Those are the two most common groups that we're going to see be protonated or deprotonated as far as solubility goes. Amines are going to be more soluble when they're protonated. Acids are more soluble when they're deprotonated. All right, so what are the factors that affect how acidic a functional group is?
Electronegativity.
Electronegativity. It's all going to come back to the same things, electronegativity and resonance. So out of these two, which one is going to be more acidic and why? We know that it's electronegativity, but more explicitly.
Oxygens.
Okay, why? It's more electronegative. So that's why.
Does it have something to do with the lone pairs? Like, does it has more to give?
It doesn't have anything to do with the lone pairs. It's just more electronegative. And if you think of the hydrogens are basically, they're trying to form a covalent bond here, right? But if the oxygen is pulling the electrons towards itself more, it's not sharing, it's not making a very strong covalent bond. The more polar the bond is, the weaker it is. The closer it is to being an ionic bond. And that's the wrong number.
No. Well, you just know that?
But because amines can act as a weak base, and we just looked at that table, all of the amines all were up in the 30s. The protonated form of the amine has its own pKa, that's 9.4.
Oh, okay.
So if it looked like this with a positive charge,
Right.
that molecule can be an acid. So I copy and pasted a number for a pKa for an amine, but the wrong pKa. The right pKa for this amine, if we're just trying to pull a hydrogen off of it, is a 38. So amines are worse at being an acid than alcohols. And conversely, what does that say about them being a base? Exactly. So if we wanted to protonate this and have it act as a base, then it's gonna have, the conjugate acid is gonna have a pK of about 9.4. And a protonated alcohol is gonna have a pKa that's down in like the 2 region. So it's pretty easy to stick an extra H plus on a nitrogen. It's not very easy to stick an extra H plus on an oxygen.
They're right next to each other on the periodic table.
But that difference in electronegativity, it's only like a 0.5, but those units, electronegativity units are kind of made up. Linus Pauling just literally like, well, we need some sort of electronegativity scale, so he just made up numbers. And so a 0.5 difference is actually a pretty strong difference. In fact, they call them the units on electronegativity don't really exist in honor of Linus Pauling. They call it degrees Pauling. But he basically said, okay, we're just gonna put the least electronegative thing, we're gonna call that 1. And the most electronegative thing, we're gonna call that 4. And then you just divvied everything up in between there. So the more electronegative something is, the more acidic it is. To a point. It's never that simple, right? Because if we go back to our chart, it doesn't have the rest of the halides on there. Fluorine is actually less acidic than chlorine, even though it's more electronegative. So it turns out the size of the atom matters a little bit. The larger anions have more space, and in general, they don't hold their electrons as tightly. Basically, there's more clouds of electrons around them, so the nucleus can't pull those valence electrons in as tight. So oxygen is more electronegative than sulfur, but sulfur's better at being an acid. Because the larger the molecule is, the larger the functional group is, the weaker the bond to that H plus. We'll see this too. We'll talk about other types of bonds, but in general, if you think about those sigma bonds, a sigma bond between a carbon and a hydrogen is hydrogen can't really be hybridized, right? Because it only has a 1s orbital to use. So a sigma bond between a carbon and a hydrogen looks kind of like this. You get some amount of overlap, but not a ton because of the shape. Well, silicon, since it's right underneath carbon, it has a 3 and n equals 3 orbitals that are all hybridized together to make the sigma bonds. And the hydrogen is much smaller in comparison. So when you make bonds between atoms in different rows of the periodic table, different energy levels, those bonds tend to be weaker because you can't get as good of an overlap. All right, so within the same row of the periodic table, more electronegative means more acidic. If you're talking between rows on the periodic table, larger atoms means more acidic. So that's why even though fluorine is more electronegative than chlorine and bromine and iodine, hydroiodic acid is stronger acid than hydrochloric acid. Because the larger anions can spread the electrons out over a bigger area.
And the more acidic they are, the easier they'll dissolve in water.
The more acidic they are, the easier it is to pull the hydrogen off. The other way to think about this that's going to be really helpful when we talk about resonance, because that's our third variable. Because it always is, right? Is you want to consider it's not necessarily about what you start with that makes it acidic, it's how stable is the deprotonated form. Right, so, and if we were looking at nitrogen again, so let's say we had our ethylamine. When it's deprotonated, what is that gonna look like? When we pull a hydrogen off,
Just an NH with a positive charge.
positive, it's now got extra electrons,
Oh. Negative.
so it's got a negative charge. If you pull a hydrogen off of the alcohol, you get something really similar, right?
Yeah.
Is it more stable to have an oxygen with a negative charge or a nitrogen with a negative charge?
And oxygen, because it's more electronegative.
Bingo. So it's not just looking at these, oh, which of these is more electronegative? That's one way you can look at it, but the other way you can look at it is how stable is my product if I pull a hydrogen off? So why is acetic acid more acidic than ethanol? They both have an OH group, right? The starting material looks very similar, right? Versus and they're both putting a negative charge on the oxygen. But your pKa for ethanol was around 16. Versus pKa for acetic acid was around 5. The only difference between these two is that there's a stable resonance structure here. And there's not a stable resonance structure here. And so because we're making something that's more stable, it's easier to pull the hydrogen off. Right, so the more resonance structures you get by deprotonating it, the more stable it's going to be. So let's practice with this real quick. Couple more slides and we're done with the new material for this week. So out of these two, the red versus the blue, which one's more acidic?
The blue, because of the double bond right there.
So what would you make if we deprotonated that? We'd have a negative there. Are there any stable resonance structures? No, because this carbon already has a double bond, right? So even though it gets a lone pair now, that lone pair can't do anything.
So then the red, because then it can go back and forth.
If we took off the red one. Put our negative charge there. Now we've got a lone pair in the allylic position, and now it can resonate around. Right, have that lone pair move there and this pi bond over to move the charge over, right? And then we can do that again. So we actually have 3 resonance structures. If we pull off the red one. We pull off the blue one, we get no resonance structures. Which is why. It doesn't have, so there are more complete tables like this. But why this. Group here is more acidic than this group here. This one, if you pull that hydrogen off, you get a little bit. And you left my water bottle in here, Christian. Look at it. If you've got one ketone adjacent to it, you got a little bit of resonance here, right? You get one resonance structure. If you've got one ketone on each side, now for this molecule, you can resonate that charge to the left or to the right. You have 2 resonance structures instead of just 1. Or sorry, 3 instead of 2. And that creates a difference in pKa of 10 pKa units. Which, and remember, pKa is logarithmic, which makes, so that would make it 10 to the 10 times more acidic. Ka is 10 to the 10 times larger.
That's a lot.
That's a lot. So 10 to the 9 is a billion, so 10 billion times more acidic. How about over here? We need to worry about resonance in the top right one.
Well, there's no double bonds. There's no.
No double bonds, so no resonance.
Yeah.
So here we're just looking at, are they different size, those atoms? Like significantly different in terms of energy level? Or are they the same energy level?
Well, the nitrogen and the oxygen are definitely different, right?
They're different from each other, but they're still in both in the second row. So when I say, are they in the same energy level, I mean, are they the same row of the periodic table?
Yes.
So we don't need to worry about the difference in size because they're both using orbitals from n equals 2. So then what's the difference between the red one and the blue one?
Whether it's attached to something that's more electronegative, and since oxygen is more electronegative than nitrogen, we're gonna want to take the red one.
Bingo. Right, the other way of looking at it is. Putting a negative charge on an oxygen is more stable than putting a negative charge on a nitrogen because the oxygen's more electronegative. And how about the sulfur versus the oxygen here? Red versus blue for the last one? Take your time, think about it.
Last one I missed.
Yeah, no worries, we're not in a rush today. Some days we are.
You've got this. You've got this. The one on the bottom. Which one do we wanna
Take off. Look at your periodic table. Because we take off the more electronegative.
If they're in the same row, we look at which one's more electronegative.
They're both hydrogen, so it's in the same row.
No.
The oxygen versus the sulfur.
Oh,
okay,
attached to.
okay.
So sulfur, it's got orbitals from n equals 3.
So which one's gonna be happy or negative?
It's the wrong way to look at
Electronegative
it.
is the larger atom.
Well, it's not wrong, but it's counterintuitive this way because that makes you think electronegativity.
So
That's true.
right, because more electronegative is the larger atom.
The larger atom is
Is
less
more acidic.
electronegative. The larger atom is more acidic because it can spread that charge over a larger space. So those 3 variables, I kind of presented them backwards. The most important, the order that you want to look at is resonance. And they're all close enough to the same strength that there's going to be some overlap. So I'm going to try not to confuse it. When you're looking at these type of questions, they're going to be, I'm going to try to write them very carefully, put it that way. So electronegativity is actually usually I can't spell electronegativity while I'm talking. Negativity. Lost a syllable in there. Electronegativity is generally the least important variable for this one.
What?
When it comes to acidity, the most important factor is, do we get more resonance by deprotonating it? And then we look at the energy levels. And then we look at electronegativity if they're within the same energy level. There is a little bit of back and forth between 2 and 3. So like I said, when I write these questions, I'm gonna make it, I want you to think about it in this order, but if it's a really extreme case, then electronegativity could wind up playing a bigger role. But I want you to think about it in this order. First, you look for resonance, then you look at what size, because those protons are so small because they don't have any electrons, right? So they're basically just glommed onto a lone pair somewhere. And the larger that lone pair, the easier it is to rip that proton off.
Okay, but the one that would be happier, more negative would be the sulfur.
Bingo. Even though oxygen's more electronegative, the sulfur is bigger, so it can spread that negative charge over a bigger area, a bigger volume technically. Mathematicians get weird when I say a bigger area and I'm talking about 3D. So technically, if a 3-dimensional area is a volume, so they can spread the negative charge over a larger volume. All right. Use the lists. So as far as this part of the chapter, the acid-base chapter goes, I can ask you which functional group is a stronger acid if I give you a table. If I don't give you a table, then you're going looking at those 3 variables. The other way I can ask a question about this is more of it ionized or deionized? Or is more of it protonated or deprotonated at a certain pH? So here's pentanoic acid. What is it going to look like in its deprotonated form?
We'll have a oxygen.
You don't have to circle the charges on these. I tend to find that especially with my negative charges, I miss them. If I don't circle them. So it's more just to remind myself that it's there. If the pKa of pentanoic acid is 4.8. And there's a solution with a pH, and we're trying to dissolve it into a solution with a pH of 3.5. Is more of it protonated or deprotonated?
Wait.
Explain why.
Because when the pH is smaller than the pKa, then it's gonna be more basic
Look that last one,
or
right?
acidic.
More acidic. Low pH is acidic, right? In low pH, if it's acidic, that means extra H pluses around. So if you have the system at equilibrium and then you dump a bunch of extra H pluses in there. Remember, if you like thinking in terms of Le Chatelier's principle, it can be helpful to write the other reactants in here out. And think about it in terms of if I started at the pKa. If I started it at 4.8 and I needed to take it to 3.5, I have to dump a bunch more acid in, right? Which is H3O plus. So if I'm dumping a bunch more acid in, equilibrium shifts the other way. So next part of this question is, if I wanted to maximize its solubility in water, would I want the pH to be high or low?
High.
High pH means we took away a bunch of H3O plus. And that's gonna push the equilibrium to the right to the deprotonated form. And if it's deprotonated, carboxylic acids have a charge, and charges dissolve better in water than neutral things. All right, so this is what it's the trickiest thing about these type of questions is that you have to think about it in levels, right? You have to start with, okay, is more of it protonated or deprotonated? And then you have to think about, okay, if it's protonated, does that make it neutral or ionized? And then you have to think, okay, if it's ionized, does that make it more soluble in my solvent or less soluble in my solvent? So you have to, those are the three questions in order to answer these. So here's another way of asking a similar question. Our solution has a pH of 6.5. Benzoic acid has a pKa of 4.2. Is the molecule more soluble in the water or non-polar solvent if the pH is 6.5? So 6.5 compared to 4.2, so it's more deprotonated. So the pH tells us it's deprotonated. The fact that it's deprotonated and an acid and a carboxylic acid tells us it's ionized. The fact that it's ionized tells us it's more soluble in water. So those are the three conclusions you have to get to get the right answer here. And we can't just jump to a high pH means more soluble in water. Because different functional groups have charges that are different based on if they're protonated or not. So when you're done writing this down, we'll do one more to show you the opposite case. Right, so carboxylic acids aren't that tricky when it comes to this question. The tricky ones are the amines. The other really common functional group to be protonated and deprotonated are amines. And what makes them tricky is that they can either be an acid or a base. You can deprotonate an amine to get a -1 charge. That's got a really high pKa. Like outside of the range with what we could do in water. Right, because water, we're pretty much limited to having pH being between about -1 and 15 or so. However, you can also protonate an amine to give it a positive charge. And that has a pKa of 9. So one of the things that can be really helpful in thinking about pH of these functional groups is to think about pH like a number line. And the pKa of your functional group is basically like your reference points along that line. If we have an amine and it's between a pKa of 9 and 38, if the pH is between 9 and 38, it's going to be in this form. If the pH is less than 9, it's in the most protonated form. And if you ever manage to get the pH above 38, we can deprotonate it all the way. Not all the way, technically there's one left, but you basically, that one's on there so well, you're never going to be able to pull that one off. Right, so it's kind of a spectrum. So for this molecule, if the pH is 11, is it going to dissolve better? Is it going to dissolve in water? So if it's at a pH of 11, it's deprotonated.
But I thought the left side was protonated.
Correct. So if it's, sorry, I pointed over here, but I said deprotonated. If pH is 11, our most common form is the NH2, the neutral form. So it's deprotonated or partially deprotonated because our pH is greater than pKa. That doesn't change, right? What does change about amines versus the carboxylic acids is for amines, deprotonated are neutral, are unionized. And if it's neutral, is it gonna dissolve better in water or a nonpolar solvent? It's neutral.
Oh, because water needs its.
Water is the really polar. So when it's neutral, it's less polar. So when it's neutral, it'll dissolve into a non-polar solvent. All right, so and these are the two biggest functional groups we see this with, and they happen to be different in their charges. Acids are charged when they're deprotonated. Amines are charged when they're protonated.
So how did you know like that 11 was neutral and not close to protonated? Cause like it's closer to 9 than 38.
It's gonna be closer over here, but it's still 2 pH units above the pKa. So if we think about this as a number line and a spectrum, we're closer to this equilibrium than we are to that equilibrium. But we're still on the neutral side of it. Does that make sense? There's also a running joke in the chemistry community. You can tell whether someone's taken a chemistry class or a history class more recently, based on how they pronounce that word. So you've taken a modern history class that's unionized, but if you've taken a chemistry class, it's unionized. Because you'd never see them in the same context, right? All right.
So then in your thought process, couldn't you have jumped from if pH is 11, it's neutral because it's on that part of the spectrum?
Correct. If you have this already drawn out in front of you. So if we were drawing something similar for benzoic acid, it would look like in our switchover is pKa 4.2, and then this side of it, it's the deprotonated form. So yeah, if you have both of your structures drawn out, you can, and you have it set up like a number line like this, then you're absolutely right, you can make that jump. But you have to do the work of looking at this first. Because the amine had it backwards, right? The amine, the pKa was at 9. And above that was the neutral form. And below that was the charged form. So there's actually a range where both the benzoic acid and the amine are soluble in water. What's the range where they will both dissolve in water? The pH range.
Eight, will it have to be higher than 9?
So if it goes higher than 9, you make this neutral, right? If we want it to dissolve in water, do we want it neutral or do we want it charged? So we want to stay below 9 to make sure the amine's soluble in water. What do we have to do to make the benzoic acid soluble in water? But not 9, 4.2, right? So if your pH is between 4.2 and 9, they'll both dissolve in water. If you drop the pH below 4.2, your amine stays soluble in water, but your acid doesn't. And if you bring the pH above 9, your benzoate will dissolve in water, but your amine won't. And so for all of these, the pKa is your most important landmark. And then you just have to think about what form is it in on either side. All right. Like I thought, about half of the lecture. And now I can let you go early for the weekend. And you can work on your homework assignment.
Do you want us to wait a little bit to do it?
It's fine. It'll take you long enough that and it's actually nothing to do with this. So you'll have to go back and remember formal charge and complete structure and skeleton. It's practice with skeletal structures and formal charge.
Okay.
So it's already review enough.
Got it.
It's only one page. It's not terribly long. It'll probably take you an hour and a half or so, if I had to guess. If I'm way off on that, feel free to let me know on Tuesday.
Okay.